that if anybody else wants to kind of build their own disassembly tools, they can begin with a small code base. It's about, I think, 3,000 lines maybe. And it includes, the binary format parsing for both ELF and PE, includes the kind of a bit of a modular instruction decoder, so later you could plug in things like PowerPC. Yes, do we have a question? No?
What language is it written in?
It's
like ANSI, C, or?
Yeah, it's ANSI-C.
Okay.
And it compiles in Cygwin and, of course, under GCC on Linux. It's actually pretty portable code. It should compile without much effort, even if you wanted to switch it over to Visual Studio as well. But yeah, so I mean, it's a good start. It's basically, you could develop a UI layer for this. You could make it interactive and jump around. It's just some good demonstration code that comes. Oh man. All right. That's used to demonstrate the initial disassembly analysis features that I was just discussing. So let's talk about a little more advanced topics. What can we do once we already have this program database built of the internal references, and how can we do a higher level analysis that will actually benefit a reverse engineer or other programmatic analysis tools in gaining a deeper understanding of how the code works. One of the best ways to prototype more advanced disassembly analysis concepts is through using IDA-Pro's SDK. I'm actually a pretty recent, I have pretty recent experience with IDA, its SDK on a plugin development front, but it's actually quite useful. Some of the documentation's a little sparse in some places, but in general, it's very usable, and IDA obviously is something that's familiar to most people who are professional reverse engineers at this time. It's by far considered the most usable disassembler and most flexible for multiple reasons. But so to take the idea of path analysis and data analysis a little bit further, I'm going to give two examples. One being Peter Silberman's loop detection plugin, which he released in the Uninformed Research Journal last issue, and a little tool that I've been working on recently that allows you to enumerate these structures within code and track references as far deep into the code as you need to. And we'll take a look at how that works. But path analyzers essentially are going to need to understand how the control flow graph looks like and recursively follow the execution flow in order to build this graph and determine all possible code paths within a specific binary. And we can group these paths by understanding which shared library calls or which sets of functionality are being dealt with within a specific code path. For example, if we're looking at a binary on Windows that's a FTP server or something, or an IMAP client, and you're looking for a specific command within that protocol and how it gets parsed, well, you simply go to where it parses the input. It will do some comparisons on if this is a, whether it be a GET command or a POST command in HTTP, arbitrary protocol. But once it determines that, and then you just look at the code flow after it's made that decision of how to treat this specific request, and you can group that functionality together. So that's the most obvious use of a control flow graph, is understanding which parts of the code do which parts of the work. And then disassemblers that don't have this ability would be linear disassemblers, and they can't determine the relationship of code blocks. That would be, Codis currently actually does not do a complete control flow graph analysis. Object dump would be the most familiar one probably to, that just does a straight linear disassembly. And here's the problem with that. Handwritten or custom assembly code can actually cause disassemblers to go awry when they're doing linear disassembly, and you don't really understand what the code's actually doing. So here's something I just wrote up really quick. It's kind of a silly example, but so we have a function right here called loc, and it just pushes a value, and then it jumps backwards 2 bytes back into the actual value it pushed. In this case, that's EBFE, which is the opcode for jump backwards 1. So it's basically going into an infinite loop. Well, our disassembler doesn't show that at all. Our disassembler basically shows that, oh, it's going to do a jump, and it's going to do some more pushes, and it's going to move, and it's going to return from the function. In reality, when you actually execute this, obviously, it goes into an infinite loop, and you never reach that code below it. So that's the most obvious drawback of a linear disassembler is you're not guaranteed to understand the actual execution path if it doesn't actually follow these jumps. And this jump right here is what I was talking about earlier, where a code flow control gets diverted, and you need to take note of that and understand that if it gets diverted, where is it getting diverted to? And in this case, you would be able to detect that it's getting diverted back into itself infinitely. So IDA builds these control flow graphs, and this is what the default output of one of their control flow graphs would look like. It's just, you obviously can see the possible data pass below the calc function here. And this is every bit of code that you need to look at within that program if you want to know exactly what calc does. Well, when we look a little bit further into control flow, one of the most common high-level constructs that we see in most programming languages are some form of loops, whether it be a for statement or a while statement or some form of understanding loops and continual execution of a piece of code for a certain length of time. And in order to speed up programmatic analysis, sometimes it's better to understand where these loops occur and understand that you only need to parse the specific section so many times, or understand that since a loop is occurring here and perhaps it's performing some string copy operation or a stircat or something along those lines, a loop is occurring and it's taking user data. Perhaps this is a location we should look at for vulnerabilities because loops are common areas where people make mathematical mistakes and the counts of the number of times you can loop, et cetera. And so let's take a little deeper look at Peter Silverman's loop detection plugin. Basically, there's two general types of loops, reducible and irreducible, and these are categorized in such a way that when you look at the control flow graph and you understand that there are pathways between two nodes in that control flow graph, that sometimes those pathways are inconsequential and they're not actually part of a loop. In this case, it's best demonstrated where B and D call back and forth into each other. There's a pathway between those two, but our actual loop is going through A to B to C to D and back to B. So a natural loop is that A to B to C to D, and we want to figure out how to eliminate the possibility that B and D should be treated as a loop, because it's actually not. It's just a reference back into the higher function. Maybe it just jumps prior to where it was. And the more complex ones are demonstrated by this one down here on the right, where there's multiple interesting pathways, and it's much less obvious of what the direct flow is in the loop that's demonstrated here. And those are called irreducible loops because there isn't a head node like the B here that can be determined as the only way to go through the loop that's represented in the second graph. But using IDA's cross-referencing, Peter's managed to develop something that can take an example, such as the one we just saw, and determine that this one does contain a loop, and that one over there, although it looks as though it has a loop and there are code paths, it does not actually contain a loop that would be interesting for software vulnerability discovery, or it's an insignificant relationship back and forth between the code locations. So we understood that execution flow analysis is generally determined by creating a graph of all possible code locations and then abstracting a little bit, observing how those paths can be taken within the code. But data analysis is a little bit more difficult because references into data, or references to data, are typically passed in registers, and they're highly variable. They may come from unknown sources. They may not be from within the file itself. So there's a number of obstacles to actually trace assembly for data reference tracking. And as far as I know, prior to my most recent research, I hadn't really seen a very good working implementation. There were a couple. There was like an ObjRec plugin, I believe, that was developed by Halvar for IDA. I had some trouble getting that working. I think there was a couple other attempts at it, but they were very initial and seemed to be a little bit flaky. So I thought about this problem quite a bit and how I would approach it, first from a static analysis perspective of how you would do variable tracing without understanding what the information was, but simply understanding the relationships between the code and when references were being made to a prior reference of a specific instance of data. So you would begin this by creating a cross-reference, a specific reference at the line of code that you want to begin tracing at. And this would be where a register or a memory location would be assigned that actual data that you're looking to trace. Following this, you would have to go through each instruction and attempt to actualize the operand values at each line to determine if these were pointing to prior references based upon what was in your tree. And so I kind of have a little, thanks to Matt Miller, he gave me a little assistance with MS Paint, and we have a little bit of a diagram here. So you would start to create these, this tree of references in the code, and when a reference was invalidated because that reference had been overwritten, you have to worry about cleaning up all the other references that were still pointing back to that original memory location or register. And so if you see here that if you were to invalidate the red block there on the right, then you would simply have to worry about invalidating the blue block that follows that. But as you get more complex relationships, you see higher up, then you have to worry about invalidating and tracking the relationship between all of the nodes that have been referenced all along the way. So you end up taking a whole lot of memory and creating very complex tree structures of references to references from within the code and understanding how to clean up all of your references when one becomes invalidated. And this can kind of be described as a combinatorial explosion scenario on large pieces of code. If you restrict it to smaller portions of code, it's more applicable, but essentially, this occurs when a huge number of possible combinations are created by increasing the number of entities which can be combined, forcing us to consider a constrained set of possibilities. It's a whole mouthful there, but essentially just means that you're going to run out of system resources before long if you're going about creating all these complex trees of relationships between data references in the code. So my approach to this was actually to take a look at using emulation rather than pure static analysis. And emulation solves a lot of the problems that we see with this because you can immediately actualize what the data references are. And if you're emulating memory allocation calls, in the case which is what I do with IDA x86 EMU, then you can actually just create boundaries within memory and watch for references from those operands that you're able to actualize to the pointer values. And so if they get dereferenced and that dereferencing occurs within the memory boundaries that you've set up to watch as structures or objects, then you begin to understand that those references are actually members of a structure or object that you're following. So as I mentioned, IDA x86 EMU is an emulator that Chris Eagle wrote and Jeremy Cooper as well. And it's kind of early in the stages of development, but I found that Chris is really easy to work with, and he's actually made a bunch of commits to the CVS within the last couple of weeks because I was working with it and we were kind of going back and forth on a few features that might have helped it work a bit better. But one of the cooler features is that it can hook the PE imports and actually load libraries, so you can trace all the way through a program without any real complexity. You basically just start anywhere in the program, and if it's going to call a shared library, it'll go ahead and load that shared library for you. And it emulates the heap allocation calls like heap alloc and virtual alloc, et cetera, so that we can create these memory references ourselves, give the return value an address that we're tracking within the heap structure that's within the x86 emulator, and then watch for the references to that. And I have a demo coming up here for that as well. This is actually the code of IDA struct, but I think we're kind of short on time, so I'm going to kind of go ahead and get to the demo here. This is the end result over here on the right. Essentially, you begin with a simple flat listing of assembly code, and as it you let it know that a certain heap allocation call is likely to be a structure, and then you just kind of let it run. So let's take a look at what that looks like. All right, that'll work. Okay, so this is the IDA x86 emulator. My code actually is all behind the scenes, and it happens completely automatic. It just simply prompts you when you get to a heap allocation call. So we're just going to run halfway through this function. And we're going to see that it's found that there's a heap allocation call right here, actually. And it's about 20 bytes, and it's going to allocate at this memory address. And if we want to track this heap allocation call, then you can see that later references within that heap allocation call are determined to be members of that structure. And there's another heap allocation call. So we've ran through half of this function.